Hi everyone, welcome back. And today we're doing this question called equal row and column pairs. So given a n by n integer matrix grid, we have to return the number of pairs such that like row something and column something are equal. So row is this, column is this. So if the row and the column is equal in any combination, we count that as one pair, and then we count how many of those pairs exist. So this is a medium question. I think it's a flat medium question, like not higher, not lower kind of thing. So, and every time when we see a grid, I think it's quite easy to get intimidated by it. But there's some tricks in when playing with the grid, and I will try to share what I've learned and used so far, and maybe it's useful for you. So yeah. So we just need to find, in this case, the row column pair would be this 277 and 277. Any other combination, we are reading from left to right and top to down. There's no other like in reverse operations in it. So some initial thoughts that we can employ is that this, like, we don't want to recreate a whole array next to it and like compare against it. But what we can do is uh we can kind of uh keep track of all the rows and see if when traversing through the uh columns, if any of the columns correspond to the rows. And if it does, we count that as a one pair. So in the first operation, what we're going to do is we're going to keep count of the rows. But the thing is, there might be multiple rows with the same sequence. Like there could be another 3, 2, 1 here. And yeah, there could just be there could be multiple combinations. So what we want to do is what this question kind of nudges us into is to use a hash map. So a hash map will be used like this. We'll take this and put it over here and say count one. If we see another one, we update this to count two. And then we put this, count one, take this, count one. For this question, each one is unique. Each combination is unique. So we traverse through the 321 has one, 176 has one, 277 has one. And what I do with this is next, I look at the columns. 312, does it exist in any of this? No, it doesn't. 277, does it exist? It exists. So we check what is the count of it. It's one. So to our global sort of variable, we add the count as one. We see 167 is not found anywhere. So it is 0 plus 1 plus 0, which is a grand total of 1. And we see it over here. But what if there's repetition? Does this solution account for repetition as well? So over here, we have 2422, 2422, and 2422. So we have so the combination of this would be, this will be one pair, and this will be another pair. Like this will be one pair, and this will be another pair. So is there anything else that I missed? Oh yeah, 3122 and this 3122. So anyways, how would our simulation work over here? So 3122, we keep count, it's 1, 1445, it's 1, 2422 will be 2. Now let's go through the columns. So column wise, 3122, it exists over here. So our count global variable will have 1 added to it. 1444 is not seen anywhere. So it's 0. Then 2422 is seen here as 2. So we plus 2. And 2522 is not seen anywhere, so it's 0. But if this were 2422, it'll be another plus 2. Because for every item that we have, we can form another 2 combination, another 2 unique combination of this kind of thing. And hence, the answer for this would be 1 plus 2, which is 3. And so with that, let's get straight to coding it out. And what I want to emphasize over here more is that think of hash map and see why it's so powerful and useful. Because we are able to store a huge long list of item into the hash map as well. It's not just strings versus key value kind of thing. You can also have other immutable objects as the key. So when I say immutable, it just means non-changeable. So in this case, we'll be using a tuple. So let me just get straight to it. So horizontal, I'm going to keep track of all the horizontal rows, and for that I'll use a for I in sorry for row in grid, horizontal row is going to be horizontal dot get row 0 plus 1. The thing is, if I do this, I'll get an error because row by default is a list, but what I need is a tuple. So what I will do is I will put R here, and then I'll put row is equal to tuple R. And now it should work. So let me just demonstrate this quickly to show you that it actually works. So if I run this now, I will get a tuple version of this. The reason why it needs to be a tuple is because we cannot have mutable objects as the key placeholder. Like as a key, we must have an immutable object, like a string or something. So yeah, if we don't have this, we will get a error when we try to run it. So yeah, row is not sorry. Okay, let's just try. So unhashable type list. So a list type is not hashable into our hash map. So okay. So now that we have a count of each of these rows, the next thing to do is to compare against the columns of each. So how do we do that? So this is where I mentioned a trick that is existing that is present in the grid sort of things. So if we do this zip and star grid, we basically transpose the entire grid such that the columns become the rows, and a call into this will just get us the sort of the column of each item, the column of each. Basically, we get each column by doing this. So for call, what do I want to do? And the good thing about this is the zip function will also return call as tuples. We don't need to make it a tuple separately. So all we need to do now is we need to have a global counter, like a count is equal to 0, and our count will just increase by every time it has seen. Like if call is existing in the hash map, we just add whatever value that is there. So horizontal dot get call 0. If it doesn't exist, so get's main feature is that if it exists, it will just return whatever it is. If it doesn't exist, it will return 0. So that way we kind of we don't need to check, like write an if else statement to see if it exists or not. We can just put a dot get and see if it exists or not. In the end, we just return count. And when we run this, it should pass both test cases. Let's submit this. Yep. Their speed is really good, but the memory is not as good, but it's fine. The memory is, honestly, I don't know. Like sometimes you might get slight variations of it. I tried a few times, and I tried the same code a few times, and I still had different memory space allocations. But overall, I think this has to speak for something like 99.88. It's whatever resource that they allocate, but it also implies that our code has been efficient. So why is it so efficient? Firstly, this operation runs on an n time complexity. The grid is n times n, like the grid space is n one side and n another side. So this is just n time complexity. And this operation itself is n time complexity. And this operation itself is another n time complexity. So it is n plus n plus n, and effectively it's 3n. And overall, it will just be n sort of effectively n. It's not exponential. It's not bypassing by becoming log n or anything. It's just n. And we cannot expect it to be better, I feel, for this question, because we have to see every element at least once to get a sensing of whether it's the same. And we can have early termination cases, but overall, this is one of the fastest way to do things. So yeah, hope you guys enjoyed that video, and let me know if you have any other comments, feedback to improve this video. If I'm speaking too fast, slow, just, I don't know, use the YouTube speed button to adjust. But I will take in mind if you leave a comment about it as well. So yeah, that is my solution, and I will see you guys in the next video. Bye.